In this video, I will be discussing about percentiles, quartiles, as well as the mean, the median, and the mode of a probability distribution. Now, let's proceed to the percentiles for continuous random variables. So, definition 9.1. Let P be a real number between 0 and 1. So, the pth percentile of the distribution of a random variable x is any real number q satisfying these two conditions, that the probability of the random variable x, which is less than or equal to q, is less than or equal to p, and the probability of your random variable x greater than q is less than or equal to 1 minus p. So, in other words, the pth percentile is a measure of allocation for the probability distribution in the sense that Q divides the distribution of the probability density into two parts, one having probability density P and the other having probability density of 1 minus P. And you can see this one graphically through a graph here. So suppose this is our rectangular plane and this is our probability distribution over the domain of the PDF. The value of Q divides the probability distribution into two parts, or into the left of this Q is having a probability density of P, and to the right of this Q is having the probability density of 1 minus P. So to illustrate this concept of percentiles for continuous random variables, we have this example here. If the random variable x has a density function of f of x, which is equal to e to the power x minus 2 for all x less than 2 and 0 otherwise, then what is the 75th percentile of x? In other words, what is the third quartile in this random variable x? Since we know that the 75th percentile is the third quartile. So, since the pth percentile is 75, then we get the p as 0.75 by dividing both sides of the equation by 100 there. So, by definition of percentile, we have p which is equal to the integral of f of x dx from negative infinity to q. So, our goal is to find the q when our percentile is 75. So, substituting our percentile of 75, which is represented by p of 0.75, we have the integral of e to the power x minus 2 dx from negative infinity to q, because our f is e to the power x minus 2. So, integrating this e to the power x minus 2, we have e to the power x minus 2. And applying the fundamental theorem of calculus, we need to substitute these limits of integration here. So, e to the power q minus 2, which is the result when you substitute the upper limit to the function, minus e to the power negative infinity minus 2, which is the result when you substitute the lower limit of negative infinity. So, 0.75, which is equal to e to the power q minus 2 minus e to the power negative infinity, because negative infinity minus 2 is still negative infinity. So 0.75 in fraction, that is 3 over 4, which is equal to e to the power q minus 2 minus 1 over e to the power infinity if you will make this exponent a positive 1. But remember, e to the power infinity is a very, very big number. So when 1 divided by a very, very big number in a limit that is already 0. So 3 over 4, which is equal to e to the power q minus 2. And transforming this exponential form to its logarithmic equivalent, we have the natural log of 3/4, which is equal to q minus 2. And solving for q, we have the natural log of 3 over 4 plus 2 is equal to q. So therefore, our 75th percentile is 2 plus the natural log of 3/4. So this is the value of the random variable for the 75th percentile here. Now, let's proceed to our next problem. If the random variable x has a density function of f of x, which is equal to 1/2 of e to the power negative of the absolute value of x, of the random variable x from negative infinity to positive infinity, then what is our 87.5th percentile of the random variable x? Now at this time, take note that the density function is symmetric about the y-axis, which means that our f of x is the same as the f of the negative x. So this is symmetric about the y-axis. So since this is symmetric about the y-axis is the center of this distribution. So the left half is just the same as the right half, and this point of reference is the y-axis. Hence, our integral of f of x dx from negative infinity to 0 is 1/2, which means that the area under the curve from negative infinity up to 0 is 1/2, because that is half of the distribution. So, computing for the 87.5th percentile Q of the above distribution, we have 87.5 over 100, which is equal to the integral of f of x dx from negative infinity to Q. So, 87.5 over 100 is equal to the integral of 1/2 of e to the power negative of the absolute value of x dx from negative infinity to 0 plus the integral of 1/2 of e to the power negative of the absolute value of x dx from 0 to q. So this is just dividing the whole range into two parts, wherein the first half is exactly 1/2 of the distribution. So instead of writing this one, we will write 1/2 because we know that this is 1/2 of the whole distribution, plus the integral of 1/2 of e to the power negative x dx, because the domain here in this integral is already positive. So we remove the absolute value that this is only negative x. So 87.5 over 100 is equal to 1/2 plus 1/2, which we factor out from the integrand, times the integral of e to the power negative x dx from 0 to q. And writing dx as negative dx, we need to multiply the whole integrand by -1 outside in order to neutralize our negative dx. So 87.5 over 100 is equal to 1/2 minus 1/2 of the integral of e to the power negative x times the negative dx is equal to e to the power negative x from 0 to q. So substituting our limits of integration using the fundamental theorem of calculus, we have 1/2 minus 1/2 of the quantity of e to the power negative q minus e to the power -0, but -0 is just 0. So 1/2 minus 1/2 of e to the power negative q plus 1/2, because e to the power 0 is 1, and distributing -1/2, we have positive 1/2. So adding the two 1/2s there, we have the sum of 1. And this will be subtracted by 1/2 of e to the power -q. But 87.5 over 100 can be written as 875 over 1000 by multiplying the numerator and the denominator by 10. So we can add both sides of the equation by 1/2 of e to the power -q. So we have 1/2 of e to the power -q, which is equal to 1 minus 875 over 1000. When you subtract both sides also of the equation by 875 over 1000. So 1 minus 875 over 1000, we have 125 over 1000. And multiplying both sides of the equation by 2, So as to eliminate the 1/2 at the left-hand side of the equation, we have e to the power negative q is equal to 250 over 1000. So transforming this exponential notation to its equivalent logarithmic notation, we have negative q, which is equal to the natural log of 25 over 100. But multiplying both sides of the equation by negative 1, we have q, which is equal to the negative of the natural log of 25 over 100. And then applying the properties of logarithm, we have q, which is equal to the natural log of 25 over 100 raised to the exponent of negative 1. But because the exponent is negative 1, we just get the reciprocal of 25 over 100, which is 100 over 25. And 100 over 25 is 4. So our q value is the natural log of 4. So this is our q in the drawing. So you can see in the drawing that our q is at the point 1.38, since the natural log of 4 is approximately equal to 1.38. So that is our 87.5th percentile for this density function of f of x. Now, let's proceed to our definition 9.2. The 25th and the 75th percentiles of any distribution are called the first and the third quartiles, respectively. And also, the 50th percentile of any distribution is called the median of the distribution. And another definition is that a mode of a random variable x is one of its most probable values. But take note that a random variable x can have more than one mode. In other words, that the mode can be seen in the graph at the highest point of the graph of the PDF, the probability density function. Now, proceeding to our next example here, we have if the random variable x has a density function of f of x, which is equal to x squared times e to the power negative bx for x greater or equal to 2 and 0 otherwise, where b is greater than 0, then what is the mode of this random variable x? So since the mode is the highest point of the density function based from our definition in the previous slide, we have to determine this highest point by using the derivative technique, which we've learned from our calculus, that the maximum value can be obtained by taking the derivative of this function and equating it to 0. So the derivative of f of x, which is equal to 0, is the optimum value of the function. So our probability density function of x squared times e to the power negative bx, we have to get the derivative of this PDF and equate the derivative to 0. So applying the product rule, we take the first factor, x squared, times the derivative of the second factor, which is negative b times e to the power negative bx, plus copy the second factor times the derivative of the first factor, which is 2x. And then obtaining their products, we have 2x times e to the power negative bx as the second product here. And this will be subtracted by x squared times b of e to the power negative bx as the first product there, which is equal to 0. So factoring our x here and also factoring e to the power negative bx, we have x times 2 minus bx times e to the power negative bx, which is the whole product equal to 0. So dividing both sides of the equation by e to the power negative bx, we have x times 2 minus bx, which is equal to 0. And then equating each factor to 0, we have x equals 0 or 2 minus bx equals 0. So solving for b, we need to add both sides of the equation by bx. So we have 2 equals bx. And then Dividing both sides of the equation by b, we have x, which is equal to 2 over b. Hence, the mode of our random variable x is 2 over b, because this is the maximum value of the probability density function. So this is the point along the x-axis wherein the probability density function is highest at that point. But since b is arbitrary, we can verify this one using a graph. Example, the graph of our PDF when b is 4 is like this. And you notice that the mode is at the point 2 over 4 because b is 4 and 2 over 4 is 0.5. And you can check in the drawing that the curve is highest at that point. So therefore, the probability is highest at the random variable of 0.5. So here, let's proceed to our next example. A continuous random variable has density function f of x, which is equal to the probability of 3x squared divided by theta cubed for the random variable x between 0 to theta. Otherwise, the probability value is 0 for some theta that is greater than 0. What is the probability of the random variable x less than the ratio of the mode to the median of this distribution? Now, let us first solve for the mode, because in this question we are asking to the probability of the random variable less than the ratio of the mode to the median of this distribution. And since for a fixed positive value of theta, the density function f of x is an increasing function, because this function 3x squared over theta cubed, where theta is a fixed constant, is a parabola opening upward. Thus, f of x has a maximum at the right endpoint of the domain interval from 0 to theta. Therefore, we say that the mode of this distribution is at the right endpoint of the domain interval from 0 to theta. Now, let's proceed to finding the median of this distribution. And we know that the median is the 50th percentile. So therefore, 50 divided by 100 is 1/2. So using the definition of the percentile, this is equal to the integral of our probability density function f of x dx from 0 to q. So in this case, we need to find the q whose area to the left of that is 1/2. Now, we know that our f of x, which is the probability density function, is equal to 3x squared over theta cubed. Then we need to integrate this function with respect to x from 0 to q, and factoring out our constant, which is theta cubed in the denominator, we have 1 over theta cubed times the integral of our 3x squared dx from 0 to q. And we know that the integral of 3x squared is 3x cubed over 3. And this will be evaluated from the limits of integration of 0 to q. Now, simplifying our integral, we have x cubed here. And substituting our limits of integration, we have 1 over theta cubed times the quantity of q cubed minus 0 cubed. And we know that 0 cubed is 0, so this is equal to 1 over theta cubed times q cubed. So multiplying these terms, we have q cubed over theta cubed. And solving for q cubed, we need to multiply both sides of the equation by theta cubed. So our q cubed is equal to theta cubed over 2. So finding our value of q, we need to raise both sides of the equation by 1/3. So our q is equal to the theta cubed over 2 quantity raised to the power of 1/3. And we know that the power of theta, which is 3, when multiplied to 1/3 is equal to 1. and the denominator is also raised to the power of 1/3. And moving it upward, we have a negative exponent of negative 1/3. So therefore, our Q is equal to 2 to the power negative 1/3 times theta. And this is the value of the random variable where we can find our median. Thus, the ratio of the mode of this distribution to its median is theta over 2 to the power negative 1/3 theta, because we have solved already our mode, which is theta, and we solve also our median, which is 2 to the power negative 1/3 theta. And canceling the common factor, which is theta, from both numerator and the denominator, we have 1 over 2 to the power negative 1/3. And moving this denominator upward, we have a positive exponent here. So this is 2 to the power 1/3, which is equal to the cube root of 2 in radical form. So this is the ratio of our mode to the median of this distribution. Hence, the probability of our random variable x less than the ratio of the mode to the median of this distribution is equal to the probability of our x here, which is less than to the cube root of 2, because the cube root of 2 is the ratio of the mode to its median of this distribution. And to solve for this, we need to apply our definition for cumulative distribution, which is the integral of our probability density function of f of x dx from 0 to the cube root of 2. And we know that our probability density function is 3x squared over theta cubed. So integrating this one with respect to x from 0 to the cube root of 2, we have to factor out first our constant outside the integral symbol, which is 1 over theta cubed. And what remains in the integrand is 3x squared here. So integrating 3x squared with respect to x, we have 3x cubed over 3. And simplifying this term, we have x cubed only. So substituting our limits of integration to this expression of x cubed, we have 1 over theta cubed times the quantity of the cube power of the cube root of 2 minus the cube of 0. And we know that the cube of the cube root of 2 is just equal to 2. And this will be subtracted by 0. So therefore, our final answer is 2 over theta cubed. So therefore, we say that the probability of our random variable x less than the ratio of the mode to the median of this distribution is 2 over theta cubed. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.